When we are given a curve as a single variable function in the form of y is equal to the f of x, we can find its lengths between a and b using this formula. But if the curve is given as the parametric equation in the form of y is equal to the f of t and x is equal to the g of t, we can find its lengths between the t values, alpha and beta, using the integration of the square root of the derivative of the x with respect to the t and a square plus derivative of the y with respect to the t and a square, and integrating this with respect to the t. So now if we're given a curve as a vector function where it has the three components, for example, f of t, g of t, and h of t, where for different values of the t, it's going to give us the vectors, different vectors. And if we trace out the ending points of these vectors, we can see the graph of the vector function. So what we're interested in is to find the lengths of this curve between the t values of the t, between t1 and tt. So if we look out to this curve as a parametric curve, we can find the lengths of this curve between t1 and t2 by taking the square root of derivative of the first component, right? It's going to be derivative of the f in the square plus derivative of the second component in the square plus derivative of the third component in the square. And we need to integrate this with respect to the t. So when we look to this term, we can see that this is nothing else as the norm of the vector function and its derivative, right? And we need to integrate this with respect to the t. So basically, we need to define the derivative of the vector function, then we need to define its norm, then we need to integrate this with respect to the t from t1 to t2 in order to find the length of the curve. So let's do an example. So what we would like to do is we would like to find the length of a circular helix, which is given with this function from this point until this point. So roughly, it looks like this. Okay, so we would like to find the length of this curve. So where the function, vector function, is going to give us in the form of cosine of t, sine of t, and t. So basically, I need to use the formula, right? L is going to be equal to the integration from t1 until t2, the norm of the r prime of t, and with respect to the t. So what we need to do is we need to find the values for the t1 and t2. So which value of the t I need to choose so that when I substitute the t, right, t1 should be something, so that r of t1 is going to be 1, 0, and 0. So probably its value is simply 0, right? So if you put the t1 to be equal to the 0 to here, it's going to be 1, 0, and 0. So which value of the t we need to choose so that the r of t2 is going to be equal to the 1, 0, and t pi. So probably t pi, right? If you substitute the t pi to here, it's going to be 1, 0, and t pi. So basically now I need to find the r prime of t. So derivative of this curve, it's going to be again a vector value function with the components minus sine of t, cosine of t, and 1. So its norm, it's going to be the square of the first component, which is the sine square of t, plus the square of the second component, cosine square of t, plus the square of the third component, which is simply 1. So which is going to be square root of t. So the length of this curve between 0 and t pi, it's going to be square root of t with respect to the t, which is the square root of t from 0 to the t pi, which is 2 square root of t pi. Okay, so now we're going to define the arc length function. Basically, if the curve is given as some vector function, r of t, what we would like to do is we would like to define the length from the starting point a until any value, until any variable t, r of t, using the function. So this function is going to be defined in the form of s of t, and this is going to be the integration from a to the t of the derivative of the r, So now let us write this with respect to the year and integrate this with respect to the year. So basically, I'm just defining the previous parameter t was the year, so that in order to define this function s. So the beauty of this function s is that, so this is going to give us the distance or the arc length of the curve starting from a until any point of the t. For example, if I would like to find the arc length of the helix at the t pi, I just need to integrate the derivative of the vector function of the helix from 0 until t pi, for example, right? And so on. So using the fundamental theorem of calculus 1, we can say that the derivative of the s with respect to the t, right? The t, which is here on the border of the integration, it's going to be simply the norm of the r prime of t. So we are going to use this result when we're going to work with the curvatures.